If you recall, yesterday we had an exercise where we looked at the derivative and used the sign of the derivative to determine the direction of the function and the direction of the derivative to determine the concavity of the function. We know that when the derivative is negative, the function is decreasing, and that the area will show us how much the function is decreasing. From there, we can, using that information, we can figure out points. Now, one of the things that we know the derivative is not telling us is where to start. So I have to provide that information. I have to say f of 0 is equal to 0. I don't actually have to tell you what's going on at 0. I just happen to do that in this case. We just have to know where the function is somewhere, because then we can figure out how it's changing from that point. So for example, I could have told you that f of 2 is equal to -3. And then we know that the function is increasing from 2 to 3 by 1. And then going backwards, we could see that the function decreased by 1 between 1 and 2. So we would have to work backwards, but we'd be going to the left. So it'd be very clear that we're going backwards. I just have to tell you somewhere on the function. Once we get the points, we know we need to connect these dots. So from there, we want to include the concavity. So notice that on the interval from 0 to 1 and the interval from 3 to 4, so on the interval from 0 to 1 and the interval from 3 to 4, oh, that's 2. Never mind. Sorry. I just confused myself. On the interval from 0 to 1 and the interval from 3 to 4, we see there is no concavity because the derivative is neither increasing nor decreasing. When the derivative is not increasing or decreasing, the function is linear. So let's see. I think in trig I was using this for the linear sections. On the interval from 0 to 1 and the interval from 3 to 4, the derivative is neither increasing nor decreasing, so the function is linear. So if f prime is neither increasing nor decreasing, then the function is neither concave up nor concave down. And that means it's linear, it's flat. On the interval from 1 to 3, we see that the derivative is increasing, so that the function is going to be concave up. F prime is increasing on the interval from 1 to 3, so the function is concave up on the interval from 1 to 3. From 1 to 2, we see a graph that is decreasing in concave up, and then from 2 to 3, we see a graph that is increasing in concave up. So there's concave up over the entire that interval from 1 to 3, but then decreasing 1 to 2, increasing from 2 to 3. And then from 4 to 5, we see that the derivative is decreasing, so the function is going to be concave down. The derivative is decreasing and positive, so we should see a function that is concave down, and increasing. The area is 1, so we see the function increase by 1. Some additional details that we'll want to include to make our graph include as many details as possible is that notice at the end when x is equal to 5, I drew the function flat. F prime of 5 is equal to 0, so f is flat when x equals 5. And that's why here I've drawn the graph flattening out. When the derivative is equal to 0, the function should show flat. So that little peak, concave increased and concave down its way all the way flat at 5. We also might want to notice that the function changed direction at x equals 2. F prime changed sign when x equals 2, so f changed direction at x equals 2. So notice that the derivative changed sign at 2, and the function changed direction at 2. And so that gives us our nice complete graph. We also know that notice that the derivative is equal to 0 when x equals 2, f prime of 2 equals 0. That means the function is flat at 2. That's how it's changing direction. It's going from decreasing to increasing. So at 2 is the moment it changes direction. Any questions on producing a graph? Looking at direction, looking at sign to determine concavity and direction. The direction of the derivative determines the concavity of the function. The sign of the derivative determines the direction of the function. How's everybody okay? Right. One of the things we had observed previously is that if two functions were only different by a constant, then they have the same derivative. So f of x plus 5 has the same derivative as f of x plus 0. So two functions that differ only by a constant will have the same derivative. Two functions that differ only by a constant term have the same derivative. This is because the derivative of a constant term is equal to 0. This is because a constant term represents a horizontal line, and the slope of a horizontal line is equal to 0. So mechanically, if I have two functions, say f of x plus 0, and another function, I haven't used red on this page, so here we go. F of x plus 5, they both have the same derivative. The derivative of 0 is 0, the derivative of 5 is equal to 0. So they both have the same derivative. Oops, the derivative of a constant term is 0. The derivative of a constant term is 0. Later on, when we're advanced calculus students, we'll say the derivative of a constant is 0, and we'll know what we're talking about. But right now, we're pretty new. So I want to make sure we distinguish between a constant term and a constant factor. The derivative of a constant term is 0. This is something that we want to remember, so we're going to reinforce it by thinking about what derivative means. And we're going to do that by saying that a constant function is a horizontal line. And the slope of a horizontal line is 0. Well, next, the idea is as many ways as possible. Don't know one way to do things, know many ways to do things. Hold up the two signs. Derivative of a constant term is 0. Slope of a horizontal line is 0. I need you to tell me the differences between these two statements. They're the same statement. I think I need to turn calculus into a bunch of TikToks and memes. And I think that would land a lot better than our current format of some stuffy old man talking to you for an hour every day. So we know that two functions that only differ by a constant term will have the same derivative. Yesterday I didn't do that. That would mean saying draw f where f of 0 is equal to 0, or a variation would be draw f where f of 0 is equal to 5. Just start somewhere else. Change the starting value. Yesterday, we played with the idea that the derivative, since g prime of x was just -1 times f prime of x. And so when we drew the graph of g and of f, we saw that the graph of g was just -1 times the graph of f. We just reflected it vertically. That makes sense because the derivative of a constant times a function is that constant times the derivative of the function. We just carry along our constant factors. So it makes sense that if f of x equals -1 times g of x, then f prime equals -1 times g prime. For h, I flipped things around a little bit and I put a constant term on the derivative. Change things up a little bit by putting a constant term on the derivative. then I ask the question is if I just add 1 to the derivative of f, are we just going to add 1 to all the values of h of x? Then I left that hanging as a question. So what must the answer be? No, right? Otherwise, I would have just made that a statement and say, see you tomorrow. But clearly, I wanted you to think about it. And you have the easy option that I would have just told you, or the more complicated option. Why is the answer no? Does that make sense? That's thinking about the meta of what's going on. That's not just listening to the words, that's listening to the tone of what's happening. Do you know what I mean? Like when we read the words, this is why text messages are so complicated, despite their simplicity. Because they just give you the words, and you might read them completely differently. Nice shirt. Nice shirt. Same message? Oh, but I use the same word. Like if you're in an argument and you have to quote back exactly what the other person said, you are losing that argument. You are in deep trouble because you have to go to a verbatim reading of what the person said. Which means you probably know what they meant. And you're just leaning into the part that you ignore. Does that make sense? If you're about to say, but these are the words you exactly, oh, you know what? I should have seen that coming. I did recognize your tone and I chose to ignore it. Do you know what I mean? So if someone uses your own exact words against you, just say, thank you. I accept your apology. And then walk away. Same thing as if they start throwing ad hominem attacks. Everybody know what that is? That's essentially, it's like, oh, well, you're ugly, right? It's like, oh, okay, so you can't, I take it you concede my point since you could not attack my idea and instead you came after me. So I accept your defeat. Here are the terms of your surrender. What I'm talking about? Derivative of constant is 0. That's the more important thing. I had to pause and talk about something else because we just dropped a very important idea on everybody, and it had to sit there for a while. It can't just be all math all the time. You have to punctuate. So, 35 minutes after the hour, I have to stop talking about math and talk about some other things to give your mind a time to rest and absorb stuff. So clearly the answer is no. Let's find out. Let's draw the graph of h of s. We've said that h of 0 is equal to 0. It looks like I wrote -0 and I was just trying to like draw the x-axis. So I'm not trying to imply that there's some other kind of 0 that we need to worry about. Let's see what happens here. There's going to be a lot more increase than decrease. So I'm going to draw 0 a little bit lower. I'm going to start 0, say, down here. There's h of 0 is equal to 0. So what we're going to notice is that h of 0, when we look at the interval from 0 to 1 on h prime, and we see that the derivative is negative. So we're going to draw a function that decreases. The area is 1. So we're going to draw a decrease of -1, a decrease of 1. Then we're going to notice that this function, or sorry, this derivative changes sign at 1/2, not at 2, like in the previous one, or sorry, 1.5, not at 2. Because I just took the same shape of f prime and moved it up 1 unit. So here, we're going to see a decrease of -1/2. 1/2, but only at the 1/2 point. So we're going to be decreasing in concave up from 1 to 1.5. And then from 1.5 to 2, we'll see an increase of 1/2. Already we can see the shape of H is very different. We still have opening linear, but that little dip where the minimum is doesn't happen at 2. It happens at 1.5, and it's a much smaller dip. And then from 2 to 3, we see this increase of 2 because there's that 1 for the square, and then that triangle part is also a 1 because it's got a base of 1 and a height of 2. So from 2 to 3, we'll see an increase of 2. So we go from here at -1, and we'll increase by 2. Then from 3 to 4, just like in F with F prime, that's not changing direction. H prime is not changing direction from 3 to 4. So we'll see a linear section on H, but the increase is going to be 3 because the area there is 3. So if I look at the increase from 3 to 4, it's going to increase all the way up to 4. Even though we have the similar shape, that shape is moved up and has essentially added 1 square to the bottom of each of those sections. And then finally, from 4 to 5, the derivative is positive. So the function is still increasing. And the area tells us by how much. It's a trapezoid, but in this case, it's a triangle and a square. So it increases by 2 more from 4 to 5. So the graph looks very different when we move the derivative up 1 unit. Notice that our concavity isn't changing though. Our intervals of increase and decrease didn't change on the derivative. So our concavity is still the same. So I still want to be concave up from 1 to 3. I'm still going to be linear from 3 to 4. And I still want to be concave down from 4 to 5. So our concavity is still the same. But the amounts of increase and decrease is very different because I moved the derivative. Any questions? Notice that for h of x, I did something different at 5. What's the difference between h of x at 5 and f of x at 5? What else did I change? F is flat when x equals 5. Should I draw h flat when x equals 5? Why not? Now, there's a smaller explanation. There's a simpler explanation for why h is not flat at 5. Yeah, we talked about why f had to be flat at 5. Why is h not flat at 5? Notice I didn't take this concave up part and flatten it out when I got to 5, like I did with f. The derivative is not equal to 0, so the function shouldn't be flat. In fact, the value of the derivative is equal to 1, so I should draw a line with this. I should draw it with a slope of 1. If I draw a tangent at 5, it should have a slope of 1. It's very iffy about whether I can draw a tangent there because I don't know what's going on after 5. But headed towards 5, it needs to flatten out to be pointing 45 degrees at 5. Scale 1, 2. So h is not flat at x equals 5 because h prime of 5 is 1, which is not 0. Despite all those faulty algebra proofs that prove that 1 is equal to 0. Any questions? How's everybody okay? Ever like the fact that I could not count to 6? Good job. Man. You know how much increase there is. I'm not good at arithmetic. Because I knew that this was an increase of 4, and I knew I just added 3 to it, so I'm going to have to say it's going to be 7 higher. It's going to be higher. So I thought, that'll be fine. Put 0 here. Any questions? Years of practice. Can't make circles though. I did practice that a lot. I don't know if you've seen on YouTube, like people that can walk up to a chalkboard and make a nice circle. I can't do that. I just have to put a dot in the middle of it and say, that is a circle. It's something like a circle. And you're like, oh, that is not a circle. That is someone whose nose is higher than their eye. Any questions? Notice the things that did change. Notice the things that didn't change. Notice the concavity was the same because increase and decrease, the intervals of increase and decrease were the same in h prime as they were in F prime. So the concavities are the same. Linear from 0 to 1 and from 3 to 4, concave up from 1 to 3, and concave down from 4 to 5. That was all the same, but the amount of increase and decrease and where the function changed direction, all that is different. How's that, okay? One more thing to go further. Notice that h prime of x is equal to f prime of x plus 1. So we clearly did not start from the same place. H prime of x is equal to f prime of x plus 1. These terms in the derivative are the same. So what should go here? X, because the derivative of x is equal to 1. So h of x is not f of x plus 1. The derivative h prime is f prime plus 1. So if we go backwards one step, because we're so good at taking derivatives now, we can even do derivatives backwards. That means that h of x must equal f of x plus x. Plus some constant that we don't care about. That's just moving things up and down. But if h of x is f of x plus x, then h prime of x is f prime of x plus 1. Notice that h of 0 is equal to h of 0 is f of 0 plus 0. H of 1 is f of 1 plus 1. F of 1 is negative 2. No, you're at 2. So the h of 1 is f of 1 plus 1. F of 1 is negative 2. Negative 2 plus 1 is 1, negative 1. And that's the value of h. F of 2 is negative 3. H of 2 is f of 2 plus 2. So I forgot where I was. Can't remember all that way back. The point is, we're not just adding x to the f of x because the derivative has a plus 1. That means our original function must have had a plus x. That's doing derivatives backwards. Any questions? How's everybody? This is always the case in math. When you learn a thing in math, you have to learn it backwards and forwards. Right after you learn addition, what'd you learn? Subtraction. Backwards addition. Right after you learn multiplication, what'd you learn? Division. Backwards multiplication. Right after you learn exponential functions, what'd you learn? Logarithmic functions. Exponential functions backwards. Any questions? Comments? Yes. This is kind of a combination of 2 and 5. This all started because I looked at that, I keep looking at that statement. When the derivative is positive, the function is increasing. And I couldn't stand it anymore because it raises the question, by how much is the function increasing? Even though no student ever asks that question. They're just like, oh, it's increasing. That means it's going up. And I'm like, oh, does anybody wonder how much? And you're like, oh, nope. It's going up. That's all that matters. I'm like, oh, let me tell you how much it is. And you're like, oh, no, stop. We don't want to know how much. I'm like, oh, it's the area. And then students are like, oh, no, not this. And then I'm like, oh, this is from chapter 5. And all of a sudden, it's no longer simple. I'm saying y'all are a weird group of people. Like if I gave you a bunch of problems and I say, here are some problems to work on, all of you work on them together, then you return them to me and I will give you points. You can all work together. I want you to help each other. Everybody would sit down there and we would make sure that you and all the people that you talk to on a regular basis have correct answers, and you turn it in and everybody gets a point. If I write quiz on the top of it, all of a sudden everybody is stressed out. Everybody freaks the F out. They're like, oh, it's a quiz. Like, you're supposed to help each other, but it says quiz on top. Ah! I stopped giving quizzes. I started, here's some classwork. And then Cam's like, oh, we call that quizzes. It's like instantly more stressful. It doesn't matter that I'm like, oh, infinite attempts. Keep going until you get it right. Ask your friends how to do stuff, but make sure that you use that information to learn stuff on your own, right? I don't care if you use your friends to help you get right answers, as long as that's not all that you're doing. If you're actually learning stuff, I think that's a win. You know what I mean? Yeah. As long as you understand the information and learn what processes we need to learn, I want you to help each other. It's like the whole point of having a society is so that we can help each other. The whole point of having professional plumbers is so that not every single person has to be a plumber. Like if I had to be my own plumber, I would start digging an outhouse because I don't like that. I'm really glad that I can call up a stranger and say, hey, my plumbing ain't working. And they're like, oh, all right, I'll see you tomorrow. And then they come and fix stuff. You know what I mean? I'm all for like independence, but not everybody should be required to know everything. You know what I mean? Because people are like, oh, well, I do my own electrical work. I do my own plumbing. That's all great. What happens if your appendix bursts? Are you going to do that yourself? All of a sudden, it's like, oh, no, I'm not independent anymore. Now I want a professional. But well, just hire the professional. If you're going to have any interactions with the legal system, hire a lawyer. You have to. They're a professional. That's why we have them. You know what I mean? And furthermore, there's nothing that I'm telling you in this class, in this whole process. There's nothing that I'm telling. There's no information that I have that you can't just go to the internet and get for free. Dr. Google has all this stuff. The Wikipedia math articles are a little bit bizarre because they're written by mathematicians, but all the information is out there. That plus Wolfram Alpha, you can learn this on your own. But you made the wise choice of hiring a professional because I can make better decisions about what questions to ask. Does that make sense? So. Anyway. That being said, one of my favorite categories of YouTube video to just chill out to is dudes that go out there into a forest and build a house. They like chop down trees and they don't talk. They're just out there in the woods, like chopping down the stuff and then like sawing and then putting logs. And then like at the end of the video, they have like a cabin. I'm like, oh, wow, that's awesome. And then they have a little dog that goes along with them. I don't know if YouTube rents out the dog for the dude that build the cabin with, but the dog is always like, I know where to sit in the camera. I know when cabin is finished building and I should run in the front door, right? If you haven't watched Cabin Being Built in Woods on YouTube, very relaxing. I don't think I've watched an actual TV program in months because YouTube is like, oh, you know what would make a great show? Person building a cabin. My other favorite is like guy washing a car. And you're like, but that one he has to talk about it, right? Ammo NYC if you're not familiar. It's like, well, here, I'm going to wash this car. It's just a dirty car. It's been sitting in a barn for like 20 years. It's like, we're going to pull it out and we're going to give it a wash. And he like talks about the whole process. I mean, yeah, it's very relaxing and informative. My car is being washed because it was raining. So that counts. Yep. All right. So those are the big ideas. Think about how the sign, direction, concavity. That's the big idea that we want to walk forward with. That's going to do it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.